I can start. So I put part of now of my lecture on slides, and then I thought that I hope that improves readability, and I will use also that left one. So where did we end it in the morning, in the previous hour? So I remind you that the issue at the time was about the completeness or incompleteness of something at times, whether the wave function is the complete objective description of physical systems, so that if the wave function changes, it's because nature is not the entire universe, perhaps. But that part of nature, the system, the state of the system changes if the wave function changes. So if I make a measurement here that collapses the wave function changes also there. That's a physical change, and that's a non-local change. And Einstein said, no, I don't like it, it cannot be, because nature is local. Nature is local because the wave function is not everything. The wave function is something. The wave function is not that the wave function vanishes. Of course, the wave function is important. Like again, in thermodynamics, you acknowledge that the temperature is not fundamental. But it's not that the temperature is useless. Temperature is probably more important than position of particles for most people. You want to know whether it's hot or cold. You don't care where the molecules are precisely. So if the wave function, it's not that it disappears, but the wave function is the dream of Einstein. Now we know that Einstein was wrong on this. But the dream of Einstein is that the wave function has a different role. It doesn't have a fundamental role. At the fundamental level, there are particles, or could be fields. But let's take a simple model of a point particle. It's not that it has to be a point particle, but it's a simple working hypothesis to start with. It's a point particle, it's either here or there, and if it's here, it's not there, and then when I see that it's not there, because it was here all the time. And then, at least for Einstein, locality is important. Again, the EPR argument, I don't go through that again, is the same story, just a little bit more elaborated. So, from the point of view of the fundamental question of completeness versus incompleteness, the EPR doesn't add anything with respect to the boxes of Einstein, so it's useless in the sense, but extremely useful because it introduces entanglement, and it really is doing the issue with to entanglement, and then that is the key feature. And it was Bell, and now we come to 1964, who understood that. Okay, so we are with Bell. So the Bell, let me help us. So the idea of Bell already, that was the end of the previous hour. The idea of Bell was to construct, so it was not happy with quantum mechanics. It was not so much happy. So things have changed from Einstein's time to Bell's time. And Bell probably was one of the brought one of these great changes. The issue was shifting in those years. So it was not so much about completeness and incompleteness, whether the wave function is everything or the wave function is only part of the story. The issue was not there that anymore at those times. The issue was about making the theory precise. If you remember the axioms of quantum theory, the theory says that the system evolves with the wave function governed by the Schrödinger equation, except when you make a measurement. When you make a measurement, it's not the Schrödinger equation anymore. It's the collapse of the wave function. So quantum theory undergoes two different, according to quantum theory, the wave function undergoes two different dynamical principles. They are both dynamical. One is more interesting, the other one is more less interesting. One dynamical principle is the Schrödinger equation, how the wave function spreads and diffuses, does what it does, when the system is left free to evolve, and the other one is the collapse of the wave function. The wave function shrinks to a well-localized state when you make a measurement. And the question is, since the collapse cannot be derived from the Schrödinger equation, since this cannot be, so the two are not, one is not part of the other. The question is, how can it be that the system goes with two different dynamical principles depending on our choice of doing something? This is not how physics works. Physics tells us that there is a universal dynamics, and that's it. So that's the matter of lack of precision of quantum theory. Quantum theory works very well, from the practical point of view. But from the fundamental point of view, you don't know when you should apply the Schrödinger equation, where you should apply the collapse of the wave function. Again, practically, there is no problem. But fundamentally, when one happens, exactly when the other one occurs, is is not specified by the theory. So the theory is not precise. And Bell has this mindset. I want to make one, so there was no issue about non-locality or whatever before. That's arriving now. Bell was thinking of making quantum theory a precise theory from the fundamental point of view, to give a precise recipe on how physical systems should evolve. And in this spirit, he was impressed by Bohmian mechanics, or the pilot wave theory, or the de Broglie bomb theory, it's called in a variety of ways, in which, according to which, let's see if I have time, as I said, the day after tomorrow. According to which, there is just the Schrödinger equation. That's it. The wave function evolves always with the Schrödinger equation. There is no collapse of the wave function. But to make sense of what happens, there are additional variables, which are the position of the particles. So there is the wave function, so you should think of Bohmian mechanics. It's not a completely correct analogy, but it's good enough. It's like, it's like a surfer on the ocean. A surfer is guided by waves. The same thing happens according to Bohmian mechanics. There are particles that are the surfer, and there is the wave function that, like water waves, guides the particles. You really should think of a surfer. And if you think, of an ideal surfer on the double slit, the water wave breaks in two parts. But the surfer, if it doesn't smash on the wall, the surfer will go either one slit or the other slit. But when it goes over the slits, there will be interference patterns because the wave recombines, and the surfer will have to balance among these interference patterns, and the surfer will not go straight anymore. It will start jiggling. No, you can picture that in your mind. That is Bohmian mechanics. So the wave function does not describe the state of the system. It's not that. The state of the system is the position. The wave function guides the system. So you see, this is an example. So Einstein was not happy with Bohmian mechanics. I will come to that. Einstein was not that, well, I can come now to that because it's non-local. It's a non-local theory. Einstein said it's a cheap solution. It cannot be that. But it's not important. Here we're talking about a matter of principle. Can we build the theory? Perhaps it's not the right one. It will be another one. But the point is, can we build a theory? That's a theory that goes in the spirit of Einstein. The reality is given by the position of the particle. The wave function doesn't disappear. The wave function is there. The wave function is important. But the wave function guides the particle. So, that was the mindset of Bell. Bell was fascinated by Bohmian mechanics because the Bohmian mechanics was formulated in the modern version by David Bohm, in the 50s. Actually, the personal history of David Bohm is very interesting because it's been basically out of place and out of time. He was in the 50s in the US, and he had two kinds of difficulties. On the working level, because he was working on Bohmian mechanics, and basically there was the standard doctrine at the time is that you shouldn't do these things. You shouldn't work on the foundation. You shouldn't work on this theory. You should work only on quantum field theory because that's the future. So he found a lot of obstacles to be, and very aggressive obstacles by colleagues that didn't like this type of research. And also, he was, on the personal level, he was a communist. And being a communist in the US in the 50s probably was one of the worst possible things that could have happened to you. Was probably, without entering into the details. So it was kicked out of Princeton. He had to move to Brazil. He had to move because he had to leave the US. He had a very difficult life on the working level and on the personal level. So he must have been really a strong character to hold on these difficulties from many sides. Okay, whatever. Bell was interested by Bohmian mechanics. But Bohmian mechanics is non-local. It's obviously, if you see the theory, it's manifestly non-local. If you have because of entanglement, if you have two particles and you touch one, you instantly change also the other. Touch one doesn't mean touch one. It means that with an interaction, you change the dynamics of the particle on the left, you immediately change the trajectory on the right, independently from distance. So it's a manifestly obvious non-local thing. And this is how I'm trying to reconstruct the way Bell worked, of course. It could be wrong. I don't think so wrong, at least. So the attention of Bell shifted towards non-locality. So can we make Bohmian mechanics local? Well, there is relativity, the nature is local, so we try to make Bohmian mechanics local. It didn't succeed. And then, as usual, smart people do, and it's a healthy way to proceed. If you cannot solve a difficult problem, you try to see whether you can solve the easy problem. So it's a good attitude. And so, Bell progressively brought down the issue to the simplest possible situation, and he came up with it. So the first situation, so I'm basically going through the original paper now, the original Bell paper. The first, we consider a single spin first. So we haven't come to another single spin. So it's just the spin degree of freedom, the spin that, and it's in a so we consider only pure states, no statistical mixture, with the ideal situation. We have, according to quantum mechanics, the perfect knowledge about the state of the system. The system is being prepared with a spin up along direction n. So I hope there are no typos in the formulas because I kind of wrote them quickly today. So it's a spin up along direction n, and then rules of quantum mechanics. Then this can be decomposed. The spin particle as a cos theta over 2 ideal states along direction A, and sin theta over 2 ideal state along the opposite direction minus A. And theta is the angle between A. The quantum probabilities, well, you know, so the probability of getting the outcome plus, so just for the notation, the probability, the quantum, so QM, the quantum mechanical probability to get the outcome plus when measuring the spin along direction A, knowing that the system has been prepared in the n eigenstate. So this is the initial state, that's the direction of measurement, and so the probability is conditioned upon these two information. The direction of measurement and the initial state is cos squared, of course, and the probability of minus is sin squared. Now the question is, the question that Bell posed, can we, so we want to build now a hidden variable model. What does it mean, hidden variable model? I want to add extra information, the extra degrees of freedom, that's what hidden variables are, an extra degrees of freedom, in such a way that I can predict with certainty the outcome of the measurement. So it's not a probabilistic description, but it becomes a deterministic description. Once I know the extra variables, I choose the direction, and I know the initial state, it won't be just probability, it will be either, well, it will be, the result, the outcome will be with certainty up or with certainty down. So determinism, and then probabilities emerge because I average over my ignorance, so I cannot control the extra information. So it's like classical statistical mechanics. I average over my ignorance and I get probabilities, but because I need to. So the first thing, that is just a question for you, let's see if you answer. So the simple thing is just to attribute a definite arrow to the spin state. So the fact that the particle has a spin up along direction n means that it's a classical arrow that is up along direction n. Would it work? This is really, the spin is like the picture that all of you probably have in mind. When you think of spin, the spin was in the So in the sense there are no extra variables. I'm talking about just this simple case. It's just n. That cat notation is just an elaborate notation to say that it is a classical arrow. Well, the answer probably, so the answer, I don't have a mathematical theorem, but the answer you say is no, you can't do such a simple model. You have to be a little bit smarter than that. Because if this is really an arrow pointing along the direction n, of course, in this way you explain why that if you measure again along n, you will find the particle there. But if you measure in a different direction, then you will have difficulties in explaining why you get sometimes one outcome, sometimes the other. So you need really to put some more information in it. It's not as naive as that a single spin is an arrow. You need to enrich the structure, otherwise you are not capable of reproducing measurements along all possible directions. And this is what Bell did. Bell did the following. So you see that now before that it's just probability, it's if probability, so we want to get rid of probabilities. But they are conditioned on the direction of measurement and the initial state. Now we don't have probabilities here. This is the outcome. It will be either +1, spin up, or -1, spin down. So it's a deterministic process. It's one of the two, no probabilities. And they are determined by the direction of measurement, the initial state, and by this extra value. So this is what I'm presenting you, and Bell states it clearly. It's a toy model. This is no one believes that nature goes this way. If there is truth in this, it must be it's a more sophisticated theory, and Bohmian mechanics is an example of that. But it's just for a matter of principle, for understanding. Okay. So there is an extra ingredient. So the wave function, we know how to control it with the Schrödinger equation. So we know how to control the wave function. A is the direction. We choose the direction, and that's the end of it. So we have to know something about lambda. In this toy model, the dynamical variables don't evolve. We don't have the equation for the dynamical variables. Bohmian mechanics provides an equation for the dynamical variables because it's a more sophisticated theory. This is a toy model, so they don't change. They are, but we know only the distribution of the random variables. The random variables are distributed, so the random lambda is assumed to be a unit vector. So here probably it's useful now to make a curved picture. Let's see. I'm not so. So lambda is supposed to be actually 3 random variables which form a unit vector, so it's 2 degrees of freedom actually because there is the constraint that the length is 1, but that's not important. So it's a unit vector which is uniformly distributed on the upper, or whatever is important, half sphere. So you take half of the sphere, or the unit sphere, it's just uniformly distributed. It's a simple one. So the area of the sphere is 4 pi, and so since it's half sphere, it's 2 pi, and so the normalized probability distribution, so it's a trivial, it's uniform. So you just have the normalization factor 1 over 3 pi. Very simple. This is the, so you again have in mind something like the particles in the gas. The hidden variables are the velocities and position. If you know the velocity and position, you can determine the temperature without measuring it. Not vice versa. If you measure the temperature, you can put constraints, but you cannot determine the position and velocity. The position are not important. The velocities. I have that picture in mind. So here. Now lambda, there are new degrees of freedom. We cannot control them. We can only know, because it's the way it is, the initial condition. And now comes the rule. So the outcome of a measurement, of a single spin measurement along direction A, on the state n, assuming that we could know the perfect value of the hidden variable, is scientific, again, it's a toy model, is the sign of the scalar product between the two vectors, lambda and A prime. I tell you what A prime is now. It's a new vector. So you see that, so this is a number. This number is either positive or negative, of course. I mean, that's not consider the case of zero measure, which is irrelevant for the model when this gives zero. That's not important. It's just elements of zero measure on the sphere, so they're not important. So this is a number which is either positive or negative, and so the sign returns either a plus 1 or a minus 1. And that's it. So you see, no probabilities. Now we see, now you have to check whether it works. We have a deterministic model that predicts unambiguously the outcome of a spin measurement for a single spin, assuming these extra degrees of freedom. No? Tell me if you cannot follow me. Purely deterministic situation. So A prime. A prime is formed in the following way. Now here I have to make a picture. So let's see. It's basically, I will draw it again here. So I take a section like that. So suppose that you have, so I'm making a two-dimensional picture now. You have N, and so I cut a section, so you have to, with a plane, I cut a section of the sphere that contains both n, the vector n, and the vector a. No? The vector n refers to the direction of the spin state, initial spin state. A refers to the direction of measurement, so that they are given as input for predicting the outcome. N and A. You see that they are here. You have N, you have A. We know them. Now, the vector A prime is assumed to belong to the same plane, so it's coplanar. It's on the same plane as, also in the picture there, as A and N, and the angle that, of course, now, you understand now why I'm making this silly model with Bell maybe, but for a good reason. So the angle theta prime that A prime forms with N is given by this relation over here. It's pi over the square sine of theta over 2. So I remind you that theta is the angle between them. No? So it's a choice. It's a toy model, but because I want to compute, I want to reproduce quantum probabilities. Nothing more. Okay, so this is how A is defined. You see that in this rule, A prime is not a new variable. It depends on A, because A is defined by the direction between N and A. A prime is in the same plane as N and A, so the remaining degree of freedom to determine this is theta prime. Theta prime is defined in terms of theta, and theta also again depends on N and A. So once you give me N and A prime is just a fictitious vector which is fully determined by A and also. Because now the interesting question is, okay, so if, now it comes the thing. So if I can control the hidden variable, in principle I could know the specific value of the hidden variable, then the outcome would be fully and completely determined. It's either +1 or -1, spin up or spin down along the direction. But we cannot control the hidden variables, that's a part of the game. And so we have to average, and that's where probabilities enter. Quantum probabilities are recovered as classical ignorance-like probabilities. We are ignorant about the state of the system. So that's a big issue. Means now we have been exposed too much to quantum mechanics that now these questions have been somehow superseded. But it's important to understand, are quantum probabilities classical or there is a difference? So, in this model, quantum probabilities are recovered as classical probabilities. I don't know the hidden variable, so I have to average. And so, the probability in this model to get, I start with the outcome minus So averaged over lambda, so this is integrated over lambda. So what do I have to do here? So the rule is that is the following one. So if I draw the vector perpendicular to A prime, what happens that in this region here, the sign function is negative. So I have to take some lambda. I take lambda, then I have to make the scalar product of lambda with A prime and decide whether the scalar product is negative or positive. Here it's negative. Here. Everywhere else here. No, tell me, I hope you are following me. But this is pure middle school geometry. So here the scalar product is between lambda and A prime. Oh, in this entire region, the scalar product is positive, and in this region is negative. And remember that the lambdas are uniformly distributed. So it can be with uniform distribution any number. So it means that the probability is given by the area, the probability. So the probability to end up here is just, think of it three-dimensional, it's the area of the sphere, I have to look on Wikipedia, it's the area of the spherical loop, it's called. If you can picture it in three dimensions, so it's a segment, so to say, of the sphere, it's a spherical loop, which is, so given the angle, of course, simple geometry, also this is theta prime, also this. So a spherical lune so the spherical lune is the intersection between the sphere, no, and two planes. You cut the sphere with two planes at an angle theta. In this case, it's theta prime. So the area is 2. Now the 2 simplified is 2 theta prime. Then you have to divide by the normalization, which disappeared, which was 2 pi. So the probability is theta prime over pi. The 2 simplifies, but theta prime is that thing over there, and so it's sine squared over of theta over 2, which is exactly the quantum mechanical probability of getting the outcome down, given the direction of measurement and the initial state. Of course, I didn't write it, but the same story happens with the outcome up. Will be just 1 minus, of course, since the sum is to be equal. So, I hope you appreciate the importance of this relation. Quantum mechanical probabilities are recovered as classical ignorance probabilities. We are ignorant about the full state of the system, we have to average, and that's probability. So, no mystery, very simple. You may say, well, I don't buy hidden variables, I stick to standard quantum mechanics. Fine, no issue, but you can choose a different way. You can go to hidden variables if you want. So this is important if you want to understand what we can say and what we cannot say about nature. So, incidentally, the book that collects Bell's paper is called Speakable and Unspeakable in Quantum Mechanics. So what you can talk about, what you cannot talk about. So you can talk about it. Okay, so, but this was a single spin particle. Can we repeat the game with 2 particles? Of course, if the state is factorized, then no big deal. The 2 particles are independent, we just repeat twice the game before. So there is no big deal. The important question is when you have an entangled state, so the 2 particles are correlated. Can you build an intervariable model? Again, I'm taking from the book, from the paper of Webb. So we consider, of course, you can consider whatever entangled state you want, but I mean the prototype is the singlet state, as we have seen in the by the way, probably I'm giving for granted in the EPR paper has been formulated in a different way from the way I presented. Because it was not considering spin, it was considering position and momentum. I don't know if you ever read the paper. The typical formulation of the EPR paper that you find, which is the one that I gave you, is due to Bohm. So Bohm, no one cared about EPR. Bohm was the first one who cared about the EPR paper and reformulated it in a more modern, in a simpler way by using spin particles. So sometimes it's called EPRB, EPR Bohm experiment, or Gedanken experiment or argument, because it's the formulation which is much simpler, given by the Bohm. Okay, so again, standard quantum mechanics. So these are the probabilities of getting outcome up in both cases. When you measure the spin, so you have Alice and Bob, not like in EPR. When Alice measures the spin along direction A and Bob measures the spin along direction B, which is the same probability for getting minus minus, and it's 1/2 square sign, and opposite anti-correlation go with 1/2 the square cosine of theta over 2. Again, theta is the angle between, now it's the angle between A and B. They can be summarized in the following way. So the quantum mechanical probability of getting outcome AB is 1/4, and we use some trigonometry, 1 minus AB cross A dot B. So this is the scalar cross, so this is the cosine of theta, and if you work on that you get the cosine of theta, and A and B can be plus or minus 1, so here you get sometimes, so you get after you get 1/4, 1 plus or 1 for correlated results, and 1 minus for anti-correlated results. This is just a way to bring the four formulas into it. Okay, this is quantum mechanics, and now the goal is, can we repeat the same game that we did before with the two entangled particles? Well, then try it. That's where the smart thing comes. Bohm mechanics is a much more complicated thing, by far. So you can recover what I'm telling you now, but it needs extra work because it's formulated in such a way that you have to describe what is a measurement, what is spin. So everything can be done, but it takes extra work. So Bell said, okay, let's forget everything about it, let's go directly to spin. Something that no one considered before. Okay, so the question is, can we redo the game for a spin particle? So the situation is this one. Again, we have two, now I put the picture. We have two spin particles, they are entangled in the single state. Alice measures along direction A, arbitrarily chosen. Bob measures along direction B, arbitrarily chosen. And the outcomes are A and B, can be plus or minus 1, spin up and spin down. Now, and here's the key question. Now, this is everything is important. The question that Bell asks, can I build a local hidden variable model for the single state? So what does it mean local? It's written here. So hidden variables is clear. We have extra variables. Now it's not n, it's equal to s states for singlet. No, this is the singlet state. So that's initial state. These are the direction of measurement, and then there are extra variables. What does it mean local? That A, what is here? A is the outcome of a measurement of the spin along direction A performed by Alice on the left particle. And as you can see, it depends on the initial condition, the quantum mechanical state and the extra variables, and depends only on the direction that Alice chooses. It doesn't depend on what Bob does. It doesn't depend on B. It is a simplified scheme. There is only A and B. So it doesn't depend on B. It depends only on B. And the same, the outcome of measurement by Bob depends only on B. It doesn't depend on A. So that's the local hidden variable. The outcome here depends only on the initial condition, which can be common. So it's the law. Entangled pairs are generated locally and then you separate them in space. So this is the common initial state, quantum plus more, and then otherwise it depends only locally on what you do here and what you do there. Locally then. And again, it's a deterministic model, because once you give me the full specification of the state of the system, then the outcome is certainly either +1 or -1, spin up or spin down, no probabilities. Probabilities, again, are recovered as average because of our ignorance. Now, let's try to build such a model. Ben proposes an example, which we will come back to this also later. So now, the hidden variables are not, they are still, so the hidden variables are still a unit vector on the unit sphere, so 2 degrees of freedom. But they are distributed uniformly. So I will come to that. So you see that it's a very simple distribution that will be important for what probably tomorrow. So just remember that it's a very simple distribution, and I have something more to tell you about this tomorrow after we do best here. What do I want to say? So, but they are now uniformly distributed on the entire sphere, not only half. The entire sphere. So the normalization constant is 4 pi, it's 1 over 4 pi in this over this sphere. And then this is the recipe. The outcomes are determined in the following way. It's again the toy model, the sign of lambda dot A and the sign of lambda dot B. So again, on the sphere you put A and B and you decide the sign, minus the sign, sorry, because you want anti-correlation. So again, A and B are either +1 or -1. Dichotomic result, deterministic model. So that's the model. Again, you are ignorant, and so you want to forget about the second half. I forgot to take it out. Now, so you can compute probabilities. Now, just to show you how they emerge, I hope that I will be able to give you just the feeling. I mean, I'm not an expert in drawing. So, this is A and the equator of A. This is B and the equator of B. Theta, the angle between A and B. And now what happens? So let's take this part here. So in this part, so if you take the hidden variable can run, it's a unit vector that can be, it's uniformly distributed everywhere here. So if it points in this spherical loom here, then the scalar product with A is positive, the scalar product with B is negative, but remember that with B we have minus. So if lambda, the hidden variable, the vector, the hidden variable points in this direction, then the prediction is that both people, Alice and Bob, will get the answer plus plus, spin up, spin up. Remember that the perfect anti-correlations are only along the same direction. When Alice and Bob measure along the same direction, the spin cannot be both up or both down. It can only be up and down, or down and up. But when it's in different directions, it can be both cases up with a certain probability. So in this region, there is a perfect correlation, up, up. And then, and the other, the other symmetric spherical loon is just the opposite, so but it's still perfect correlation, minus minus. Here, in the part above, you have plus minus. Oops. And here you have minus plus. So this is the no, I went in the opposite direction, sorry. I have to go up. Okay, so here. Okay, so this is how distributed. So since the hidden variable again, so this is how the signs are distributed in the unit sphere. Let me just this how the sphere is divided. So since the distribution of the hidden variable is uniform, the probability is just given by the surface, the area, and then the area is again. It's the spherical, so for plus plus, and also for minus minus, it's the spherical loon, which is again 2 theta. That's the area of the spherical loon, divided by the normalization 4 pi, so this is theta over 2 pi. And then the other one is just a complement, so it's 1/2 minus theta over 2 pi. These are the predictions. And then Bell points out something that now that I'm telling you, it's embarrassingly trivial and obvious, but now you have to remember that at the time, he was the only one who thought about it. I reported, there is one more bracket. I have reported the quantum mechanical probabilities. So you see that in this hidden variable mode, this is the key point of Bell. This is where now it starts going behind what was known at the time. The key observation of Bell, which is obvious by the formula, is that if you choose the same direction for Alice and Bob, then the angle is theta is 0, it's the same direction, and this hidden variable model is capable of reproducing the quantum mechanical behavior. Perfect anti-correlation. So, and remember that, of course, it's a trivial, obviously, but remember that in the EPR, in the version, in the EPR paper, they were concerned about, just about anti-correlation. If I measure the spin here, then I know that this, and it's up, I know that on the opposite side, the spin will be down along the same direction. So this is the striking point. The striking point of quantum mechanics is that the anti-correlation along the same direction, because along different directions, apparently nothing interesting happens. It's just random events. That was the understanding at the time. But Bell, no, goes behind, and that's the content of Bell theory in a way. Bell goes, no, look, I'm interested only also what happens along different directions. And my hidden variable model, obviously, is not capable, this is different from that, is not capable of reproducing the quantum mechanical prediction. It reproduces the quantum mechanical prediction along the same directions, but is not capable of reproducing the quantum mechanical prediction along different directions. Now we come to the question. He also Bell notes that with the non-local hidden variable model, and Bell he was not able to do any better. But he notes that with the non-local hidden variable model, it's very easy, in these toy models of course, to recover the quantum prediction. Here you have. So this is not, so B is local, because the outcome depends on outcome for Bob on the right, depends only on his choice of direction. But this is non-local for A, because the outcome of the measurement in A depends not only from the direction chosen by Alice, but also the direction chosen by Bob. So it's a very non-local model, and the argument is so. Oh, I shouldn't have put the minus here, sorry. This is a plus. It's a type. It's like before, it's plus and minus, but the only difference is that it's the same formula as before, but with the crucial difference that is not A anymore, but is A prime, so it's a different vector, where A prime is coplanar to A and B, also and B, and it's such that theta prime, the angle, between A prime in A is 1 and minus, is such that the following relation holds. Let me just control one thing. Yeah, no, so theta prime, sorry, is the angle between A prime and B. So you have to, so the model is the same as before, but you have to replace, for the first measurement, you have to replace A with A prime. And A prime is controlled by A and B. So it's a non-local model. Now I don't go through the calculations, but let me see, yes. Now I don't go through the calculation because it's the same story as before, but you can easily prove that with this choice, it's made ad hoc, so there is no surprise, you can predict the quantum mechanical probabilities for the single state. So, what does it tell you at the state of the art at the moment? It tells you an important thing, that even for the singlet state, you can interpret the quantum probabilities as classical ignorance probabilities. The model is there. But you are paying, at the moment, you are paying the price. But the model is non-local. What happens on one side heavily depends on what is done on the other side. Non-local is a variable model. And now Bell, it's always the same paper, and then I'm going to finish soon. And then Bell asks the question. So you should think of really being in the shoes of Bell. So Bell was starting with volume mechanics, it's too complicated. I want to make a toy model. I succeed with one spin. It seems I'm not capable with two spins in a entangled state unless I give up locality. And then Bell asks himself, but am I idiot? Am I that I'm not able to see how to do the model? Or is it impossible, as a matter of principle, to build a local hidden variable model? And the answer was Bell's inequalities. The answer is no, it's not that Bell was not capable, but you can't do that. This is the content of Bell, which is summarized in this diagram. I will present it to you tomorrow morning, Bell's theorem, for those of you that don't know. So the summary is the following one. The summary, that's what Bell proved. So the Bell's theorem, what is called Bell's theorem, is composed, that's one way to look at it. It's composed of two parts. One is EPR. EPR, if you remember, that was my drawing at the board. The EPR argument says that locality plus the quantum mechanical correlation, so if you buy quantum correlation for entangled systems and you force locality, then you have incompleteness in the variables. Local hidden variables, that's incompleteness. The contribution by Bell is that the local hidden variables lead to inequalities. We will see them tomorrow. So local hidden variables lead to inequalities, which are Bell inequalities. Now what happens? That quantum mechanics violates the inequalities. So quantum mechanics negates this, violates the inequalities. And then you go back. So if the conclusion is wrong, it is because at least one of the two hypotheses is wrong, no? Now, this is not wrong, because this has been repeatedly proved in experiments, correlations. This has been repeatedly proven in experiments. So you cannot negate this one, because it's empirical evidence. Then it remains this one. That's Bell's theorem. The violation of Bell inequalities, this is an important statement, the violation of Bell inequalities implies non-locality. So, quantum mechanics violates Bell's inequalities. That means that you cannot reformulate quantum theory in terms of a local theory. What does it mean? Again, take the classical situation of the box, two boxes, one with the blue particle, one with the red particle. One box here, classical situation. One box there, probability, 1/2 and 1/2. You open here, you find the blue particle, then the red particle is there is the red particle. Probabilities change instantly. This is a classical situation that can be described with local physics. The colors were already there before. So you can give a local explanation of this situation. With quantum mechanics, it's not possible, because quantum mechanics violates Bell's theorem. So if you build a local model, the local model will satisfy Bell inequalities, which means that this local model will not be able to reproduce quantum probabilities. You have to choose one of the two. If you want a local model, you cannot reproduce quantum probabilities. If you want to reproduce quantum probabilities, you have to accept that no locality. That's the theory, and you have to come to experiment. So I'm telling you only about the theory, with relation to quantum mechanics. Quantum mechanics is a non-local theory in a strong sense that any way of reformulating the theory by reproducing the quantum probabilities will end up in violation of Bell inequalities, which means non-locality. Now experiment comes. So quantum theory could be wrong. And instead it seems to be right. Experiments prove the violation of Bell inequalities, which means not that quantum mechanics is not local, but the nature is not local. Now it's not a matter of quantum mechanics anymore. If you build, so now forget about quantum mechanics. Quantum mechanics never exists. Well, spin exists in a sense. So you can forget about quantum mechanics. You can think of a universe where just the spin, whatever it is, spin arrows, whatever it is. The word spin was not invented in quantum physics. The word spin means to spin. So it's a classical spin. Something. Also classical something can spin. So forget about quantum. It's a theory that can of a universe that describes at least two spin particles in some state that we call entangled, but it's not a cat, it's not quantum. We call it that way, but it's whatever it is. The theory, if wants to agree with experimental evidence, it must violate Bell inequalities. Violating Bell inequalities means violating locality. Nature is non-local. What it means that nature is non-local, we have to well. Here it comes to frontier research, which means that there is a degree of subjectivity in the statement. So it's, I will present you also my personal point of view on the topic. Non-locality is not being understood what it means with non-locality, but there are some things that are clear. And then we'll come to it. So before terminating this lecture, just a warning. If you go on Wikipedia, for example, very often Bell's theorem is presented in this way. This is Bell's theorem. It's presented in this way, that these three assumptions imply the violation of Bell inequalities. EPR correlation, locality, and hidden variable. This, the first and the third, it's what people refer to with the ugly word, local realism. Locality, realism means the real stuff, hidden variable. Local realism, correlation of course, implies Bell inequalities, which means that the violation of Bell inequalities, you can give up, well, again, this is experimental evidence, you cannot give up. Violation of Bell inequalities means that you can give up either this or that. But in particular, it implies that you can give up hidden variables and retain locality. This is wrong. It's clearly wrong. Bell's theorem is this one. Also, it's not because I say this. It's Bell that says it. Hidden variable was never, so Bell was clear about that. He calls it determinism. It means hidden variables. Hidden variables was never an assumption of the theory. So you don't have to trust me, you can read Bell's paper. So this is not an assumption. This was a consequence of the EPR part of the story. This is Bell's theorem. The violation of Bell's theorem, in a strong sense, implies non-locality. We live in a non-local world. It's not my fault. That's what experiments say. And we have to accept that. After it would be an interesting way of looking. We will give you a way to look at that. Okay, so I Oh, no, so I can tell you a reason why. This is, now we go, and then I finish, in a little bit of psychology. So why do people end up in this? Because relativity is so much rooted in our understanding of physics that some people are willing of doing anything to save relativity. Einstein, first one. And there are good reasons. I have nothing personal against relativity. So, you give a, so let me just be a bit ironic. So, if you take so if you think local realism, you want to give up realism for locality. What does it mean? If you give up realism, that nothing exists, but it's local. So it becomes a kind of an ironic way to look at, to think of nature. But jokes apart, this is not very serious. The motivation for the Nobel Prize says that the guys there, Aspect Klauser and Zeilinger won the Nobel Prize rightfully because they, with the checking the evaluation of Bell inequalities, they disproved hidden variables theories. No, it's wrong. Hidden variables theories have not been disproven. There are on the market more mechanics. So even the Nobel Prize committee did not understand the meaning of that. But they gave the correct Nobel Prize. Just a motivation that is. I'm not arguing against the Nobel Prize. I want to be clear. The Nobel Prize, they deserve the Nobel Prize. But the proper motivation was not the right one. Hidden variables have not been disproven. You can add hidden variables model, the points that they have to be moved. And then what to do. Okay, so I end up here. So tomorrow morning we go through Bell's theorem to understand how it works. Okay, thank you for your attention.